Every market data pipeline eventually asks one question: is this feed late? Answering it honestly means separating real transport delay from the error in the clocks that measured it. A source stamp and a consumer ingress stamp bracket everything in between, and a clock gate decides whether the result can be trusted at all. Get that separation right, and you can state freshness with evidence instead of a guess. Here is what we will build together. We will name the 3 timestamp owners, calculate the observed latency components, preserve a negative latency instead of hiding it, and verify the eligible percentiles in both Python and TypeScript. Point-in-time discipline runs underneath all of it. What is known later was not known earlier. 3 boundaries own 3 stamps. The venue encoder stamps the source event time. The consumer's network card stamps ingress. The moment the packet arrives. Indiana's the feed handler stamps ready when processing finishes. Adjust the source-to-ingress duration measures everything between the first 2 stamps. But without intermediate stamps, we cannot split it into network versus vendor. We report observed source-to-ingress, never a hop we did not measure. The measured duration equals the physical duration plus the receiver's clock offset minus the source's clock offset. When the 2 clocks disagree, that difference leaks straight into the measurement. And drift means the offset is not constant. It changes through time. The equation stays mounted. Only the offset terms move. Take one event. Source-to-ingress is 20.842 milliseconds. Processing adds 0.934. Together, that is 21.776 milliseconds observed end-to-end. The clock profile declares a bound of plus or minus 0.05 milliseconds, so the defensible range is 20.792 to 20.892. Now one event appears to arrive 0.7 milliseconds before it was sent. That is physically impossible. It is clock error, not speed. The wrong response is to clamp it to 0, or take its absolute value. Keep the signed value, mark it as a clock error negative latency, and exclude it from the percentiles. A visible impossible number is safer than a plausible lie. Some events sit right on the edge. If the clock error interval straddles the warning threshold, neither a pass nor a fail is defensible. We label those threshold uncertain and exclude them, rather than pretend the bound is sharper than the clocks allow. The implementation validates the clock profile first, subtracts integer microseconds, classifies in a fixed order, then summarizes only the eligible values. In TypeScript, the subtraction happens in BigInt before any conversion to a float, so we never lose microseconds to rounding. Python and TypeScript share one fixture, so either can expose drift in the other. Why care? In 2012, an SEC release documented feed path disparities at the New York Stock Exchange, but that release does not publish the event-level timestamp chain, so we use it as motivation, not as data. Fact: missing evidence and decision stay in separate boxes. We never fabricate timestamps to fill the gap. Run the canonical corpus, and the numbers are exact. A 99th percentile observed latency of 21.84784 milliseconds, 1 negative clock error state, and 1 independent sequence gap. Latency and completeness are different questions. The gap is counted separately from the tail. So, own your timestamps, bound the clock error, preserve impossible observations instead of erasing them, and keep latency separate from completeness. Do that, and whether the feed is late becomes a statement you can defend. Next, we will build the price source consensus check. Keep building with the Fintech Builder